Welcome in Core. Have you ever thought about interstellar travel? It sounds romantic to journey to other world towards the stars, but actual reality might disappoint you. The current maximum speed of the Voyager 1 probe is 10.5 meters per second. Even at this speed, the journey to our closest star, Proxima Centauri, would take about 74,600 years. Now imagine that one day humanity creates spacecraft capable of traveling close to the speed of light. About 186,000 meters per second. Sounds impressive or maybe just impossible. But even that wouldn't be enough, because even at that speed, if we wanted to leave the Milky Way galaxy, it would take around 100,000 years. And what if we wanted to go further and consider not just interstellar travel, but intergalactic travel as well? That's where an even more serious problem emerges. Namely, a gigantic cosmic anomaly that was discovered in 2013. While conducting research, a group of astrophysicists found that our galaxy is surrounded by a massive cosmic void, which according to laws of physics shouldn't exist. This isn't just a region with a lower matter density. It's one of the largest known cosmic voids. Its diameter could reach 2 billion light-year. If it were filled with galaxies, it would fit more than 20,000 Milky Ways lined up from edge to edge. The scale of this anomalous region is truly staggering. Light would take 2 billion years to cross it. But perhaps the most shocking part of this discovery isn't the size of the void. It's our location. We're most likely located close to its center. Our galaxy seems to lie at the heart of a colossal funnel. And as scientists note, that could seriously affect our understanding of the structure of a universe. But if we really do live in a special isolated corner of space, an inevitable question arises. What lies beyond it? Could the space beyond this void be fundamentally different in density, in structure, or even in the laws of physics that govern it? Today, more and more scientists are wondering what would happen if we could cross that boundary and see the universe as it reveals itself on the other side of the void. Locals hold this was one of the most mysterious cosmic anomalies discovered in recent decades, named the KBC void. When astronomers Ryan Keenan, Amy Barger, and Lennox Cowie first proposed the hypothesis of its existence, it caused a true shock in the scientific world. This is not just a patch of thin space. It's a violation of the very order of the universe as we know it. But what exactly is this void? And why could its existence change our fundamental understanding of a universe? To get to the bottom of this, we need to look into the past, the distant past. Rewind to about 13.8 billion years ago, to the moment when it all began. The Big Bang. The universe began expanding suddenly, rapidly, in all directions at once. At that moment, energy expands evenly like ripples in water after you throw a pebble in. It's believed that matter was disturbed just as evenly. This is the basis for the so-called cosmological principle. The idea that on a very large scale, the universe should look the same in all directions and in all places. After all, matter should have spread out uniformly. Because of this, we can apply the same physical laws to nearby stars and to objects at the edge of the observable universe. Because the way things work here should apply everywhere. At least that's how it was supposed to be. But data from recent years increasingly show that matter in the universe is unevenly distributed. Different regions of space contain areas of higher and lower density, which means the idea of cosmic homogeneity is already in question. But the structure of the KBC void stands out even with this context in mind. It's not just a less dense region, but an anomalously vast area in which some of the laws of physics may be different. Research shows that the KBC void has an approximately spherical shape and may extend up to 1 billion light-years in radius. That's 4 times larger than the linear Ka supercluster, which contains about 100,000 galaxies, including our own. These vast dimensions account for roughly 2% of the entire observable universe, making the KBC void the largest known cosmic void. But calling it truly empty would be inaccurate if only because we're in it. Indrail Barnick, a postdoctoral research fellow at the University of St. Andrews who studies the KBC void, conducted calculations and found that the matter density in the form of stars and galaxies within the void is about 20% lower than outside it. At first glance, the difference may seem small, but within the framework of cosmic laws and the vast scale of this void, it's something extraordinary. For unknown reasons, the universe has formed a gigantic spherical region where stars and galaxies are far less frequent than beyond its boundaries. Paradoxically, It's this very anomaly that, according to scientists, might help answer one of the biggest mysteries of modern cosmology: why the universe is expanding faster than it should. After the Big Bang, the universe began expanding rapidly, and that process continues to this day. The speed at which this happens is called the Hubble constant. To measure it, scientists use two main methods. The first is based on observing relatively close cosmic objects, supernovae, and galaxies. By measuring how quickly they are moving away from each other, astrophysicists get a value of 45 meters per second per megapark. In other words, every second the distance between objects about 3 million light-years apart increases by 45 miles. Music, the second method, goes deeper. It relies on the study of the cosmic microwave background, the ancient radiation that arose shortly after the Big Bang and is still spreading throughout the universe. This light has been traveling to us for about 13.6 billion years, providing scientists with something like a snapshot of the young universe. Based on this data, scientists are working on reconstructing a model of what the early universe was like. From that, they calculate how fast it should be expanding today. And this is where things get strange. The results from this method give a completely different value, around 41 meters per second per megapark. That's lower than the results from the nearby galaxy method. This discrepancy has its own name, the Hubble tension. If we only look at data from the cosmic microwave background, the universe should be expanding more slowly than what we actually observe. But direct observations tell a different story. The galaxies around us are moving apart about 8% faster than the physics of the early universe would allow. Astronomers haven't yet agreed on exactly what causes this discrepancy, but more and more specialists believe the key might lie in our cosmic environment, in the KBC void itself. And the explanation might lie in gravity. We know that massive objects like stars can pull in less massive bodies, planets, asteroids, and comets. And it seems the same principle applies here. The denser regions beyond the void are pulling on the galaxies inside it. It's as if they're trying to drag them out of the void, adding extra acceleration on top of the universe's natural expansion. This gravitational imbalance could be exactly what's distorting our measurements. Brian Kating, a cosmologist and physics professor at the University of California, San Diego, considers the void hypothesis quite plausible. In his opinion, it really could explain why the universe is expanding faster than expected. But as he himself admits, that there are plenty of questions remaining. One of the main ones is, how far does this void's influence actually extend? If its effect is limited to just our part of the cosmos, then it only explains a discrepancy locally, which means a global problem is still unresolved. It would truly eliminate the Hubble tension. In addition, Kating points out that Banach's theory depends on which void model is used. Different models produce different results. They predict different galaxy behaviors and different impacts on the overall flow of matter in the universe. In the end, this is still just an approximation, a simplified picture. The void might be far more complex than it appears. But before we can talk about the effects of the void, we first need to understand how large it really is. And the problem is, recent data suggests the KBC void may be much smaller than previously thought. One scientific research group analyzed the cosmic flows for Catalog, the largest database of galaxy distance measurements. They used the Tully-Fisher relation, which estimates a distance by comparing a galaxy's brightness with its rotation speed. According to their calculations, the size of the void is about 230 million light-year. That's almost 10 times smaller than earlier estimates. Of course, this doesn't mean that the gravitational acceleration effect goes away, but it's no longer strong enough to fully explain the discrepancy in the universe's expansion rate. So, the question remains open. The void most likely exists. Scientists are nearly certain of that, but it remains unclear how big it is. It might occupy up to 2% of the observable universe, or it might be far more modest in size. What's more, the data from the DESI project between 2023 and 2024, which maps the nearby cosmos in ultra-high resolution, suggests that these kinds of voids aren't rare. It's possible that our local void isn't unique at all, but just one part of the broader cosmic landscape. But don't think that this makes the universe any less exciting. On the contrary, the KBC void is raising more and more questions among scientists. Astrophysicists are interested not only in its potential role in resolving the Hubble tension, but in a far more intriguing scenario. What if we weren't inside this void, but outside it? What might the cosmos look like then? What would change in our observations? And most importantly, how would our view of the universe itself be different? Of course, the boundaries of this void are at such colossal distances that for humanity, reaching them will likely remain forever unattainable. But let's imagine we had unlimited time and access to technology that allows near limitless movement through space, pushing the edge of physical laws. In that case, buckle up. It might get a little bumpy. The journey beyond the KBC void. This journey would require a spacecraft of an entirely different technological level, capable of withstanding enormous acceleration forces and shielding passengers from one of the main dangers of space, radiation. But the most important requirement, the ship would need an unimaginable speed. Without that, the journey would be practically endless. For instance, if the ship's maximum speed matched that of Voyager 1, currently moving at about 10.5 meters per second, it would require immense patience. At that speed, you'd leave the solar system in 33.5 years, and it would take about 74,600 years to reach the nearest star, Proxima Centauri. Not a very inspiring prospect, especially considering that Voyager 1 is one of the fastest human-made objects ever built. So, let's imagine we have a radiation-shielded ship capable of far greater speed and unlimited time. In this case, our ship launches from Earth towards Proxima Centauri, but there won't be any instant acceleration like in the movies if you want to survive. Of course, the human body can withstand acceleration in the range of 4 to 6 g, 4 to 6 times Earth gravity, and even then only for a limited time. As the load increases, blood flow is disrupted, especially to the brain, if you try to accelerate to the speed of light in just a few seconds. Like in Star Wars, you'd experience over 6000 g, which would literally turn you into a human pancake. Let's say the ship accelerates at a constant rate of 1 meter per second every minute. In the first minute, you'd be moving at 1 meter per second. After 10 minutes, it's 10 meters per second, and so on. This way, in just about 13.5 days, you'd reach the boundary of the solar system, the helo, where the solar wind ends and interstellar space begins. That's significantly faster than Voyager 1 and 2, which took 35 and 41 years to get there. You'd make the trip in less than 2 weeks. By the time you leave the solar system, the ship will be moving at about 19,300 meters per second, or roughly 10.2% the speed of light. By human standards, that's an incredible speed, but on a cosmic scale, it's still just a crawl. Out here at the edge of the solar system, communication with Earth becomes severely limited. A radio signal traveling at the speed of light would take nearly 17 hours to reach Earth, and the reply would take just as long. That's 34 hours for a single message exchange. No longer a dialogue. More like texting a girl you like and being left on read than nothing but silence for almost a whole day. You keep moving forward into the dark abyss. The sun behind you is now just a bright dot among billions of others. Meanwhile, your ship speed continues to rise. After about 65 days, you reach half the speed of light, 93,000 meters per second. At this point, the ship is roughly 260 billion miles from Earth. That sounds like an enormous distance, and it is, but only by Earth standards. On a cosmic scale, it's still quite small, just about 4.4% of a single light year. However, at this speed, effects of relativistic time dilation predicted by Einstein start to show. According to relativity theory, for objects moving at high speeds, like our ship, time slows down relative to an observer at rest. This is called relativistic time dilation. What does that mean in practice? While 65 days have passed for observers on Earth, less time has passed on board the ship. Your onboard clock starts falling behind Earth's. And the closer your speed gets to light, the more noticeable this effect becomes. At around half the speed of light, time dilation becomes quite noticeable. Everything including biology, clocks, even your sense of time changes compared to what's happening on Earth. According to special relativity, at 50% of the speed of light, every 10 hours on Earth corresponds to 8.5 hours on the ship. But if your goal is to reach the edge of the KBC void, that's not enough. You must keep accelerating. Soon, the ship reaches 90% the speed of light, about 168,000 meters per second. Time on board slows down to 43.6% of Earth time. In other words, every hour on Earth feels like only 26 minutes for you. Time starts working in your favor. A special moment comes on the 129th day of the journey. According to calculations, the ship has traveled about 1 trillion miles. You've reached 99.99% the speed of light, and going faster simply isn't possible. In the scientific community, it's practically a universal law. The speed of light is the absolute speed limit in the universe. Only massless particles like photons, radio waves, and gravitational waves can move at that speed. Any object with mass would require infinite energy to reach light speed. A good example is the Large Hadron Collider. In it, protons are accelerated to nearly the ultimate limit, 0.99991 times the speed of light. That's about 299,792,455 meters per second, just 3 meters per second short of the maximum possible speed. You might ask, why not just push a little harder to gain those last few meters? Just increase the power slightly. But nature is unforgiving. To overcome those final 3 meters per second, you'd need more energy than exists in all the stars of the universe combined. This isn't an engineering limitation. It's a fundamental property of space and time. The speed of light isn't a goal. It's a wall, and that wall is impenetrable for anything with mass. In nature, particles can approach the speed of light, but never cross that boundary. And in 1991, scientists observed something truly extraordinary, a particle that came to be known as the Oh My God particle. And believe me, that name didn't come out of nowhere. The particle was moving at a speed equal to that percentage of the speed of light. Nothing ever recorded had moved faster. Its energy was comparable to that of a baseball flying at 58 miles per hour. It's hard to imagine a subatomic particle invisible to the eye racing through space near light speed with enough energy to punch through a hangar door. And it's a perfect example of what happens to objects as they approach the speed of light. Their energy increases exponentially, rapidly, almost terrifyingly so. So, our ship traveling at 99.99% the speed of light becomes one of the most potentially destructive objects in existence. Theoretically, its energy could exceed the power of a supernova explosion, which raises a natural question. What if the ship actually reached the speed of light? According to relativity theory, the mass of an object moving at that speed would become infinite. And to accelerate something with infinite mass, you'd need infinite energy. But in our universe, infinite sources of energy don't exist. Put simply, the physics breaks down. Reality collapses under the impossible strain. That's why nature imposes a hard limit. No object with mass can ever reach the speed of light. So our ship continues moving at 99.99% the speed of light. And from this moment on, everything changes. According to relativity theory, at a speed like this, time aboard the ship slows down by a factor of about 70 compared to Earth time. You won't notice it yourself. Your clock ticks normally. Your heart beats at a regular pace. You live your normal life. But for observers on Earth, everything appears to happen about 70 times faster. This effect becomes especially clear as you approach Proxima Centauri, located about 4 light years away. At nearly light speed, the trip should take 4 years from Earth perspective. And sure enough, for those who stayed behind on Earth, that's exactly how much time goes by. But for you aboard the ship, it passes in just about 21 days. It sounds like a paradox, but that's how relativistic physics works. Time dilates and space contracts. To you, it's as if Proxima moved much closer. The journey continues. 1,414 years have passed on board. During that time, you leave the boundaries of the Milky Way galaxy. But on Earth, around 100,000 years have gone by. The people who saw your ship take off have long disappeared. Perhaps even humanity itself is gone, and you're still going. Finally, after crossing 230 million light years, you reach your goal. According to the ship's clocks, 3.25 million years have passed. Right here, according to current astronomical data, begins a mysterious boundary of the KBC void. You've arrived at your destination. Beyond this vast empty region, space begins to noticeably change. Based on astronomical studies, the matter density increases by about 20%. If galaxies used to be sparse, they now become increasingly frequent. Scientific models suggest they cluster more densely, forming chains, groups, and massive superclusters. This is the large-scale structure of the universe. Space becomes more dense. It's reasonable to assume not only the amount of ordinary matter increases, but also dark matter, which is thought to be responsible for forming and attracting these galactic structures. Gravity here is likely stronger, potentially affecting your ship's motion. To continue flying, you now need precise navigation, accounting for the mass and layout of surrounding structures. This is no longer the quiet, empty part of the cosmos. Hey, everything moves, intact, and pulls on everything else. And yet, as you pass through these dense regions, it becomes clear what we see may only be the surface. Something mysterious lies hidden further out, deep in the cosmic dark. The universe is larger than we can comprehend. Currently, we know there are at least 100 to 200 billion galaxies out there that we can now see. But it's a good chance there could be 2 trillion galaxies or more in our observable sphere alone. We just can't see them. We all know that the observable universe is estimated to be approximately 13.7 billion years old. This is defined by the speed that light travels. And astronomers came up with the age of the universe by measuring light that has reached us from the oldest and most distant stars. We define observable space by the light that has reached the Earth and can be seen. Cosmologists estimate the oldest photons we can currently see have traveled a distance of 45 to 47 billion light-years since the hotly debated Big Bang theory. This means that our sphere of observable universe is around 93 billion light-years across. To give you an idea how big that really is, 1 light-year, which is a unit of astronomical distance that light travels in 1 year, is 9.46 trillion kilometers. With that in mind, the big question is how can the universe be 93 billion light-years across if it's only 13.7 billion years old? This means that the universe could be older much more than 14 billion years. We know that anything further away from the light that we see from the beginning of the universe or the cosmic Big Bang hasn't had enough time to reach us. Thus, we can't see what's out there. It's pitch black. But does this mean the edge that we can see is all there is? The truth is there could be a lot more out there. Ever since the Big Bang, the cosmos has been growing at an increasing rate. It was Edwin Hubble that discovered that the universe is expanding and that all galaxies are moving away from the Milky Way. Not only are these galaxies moving away from us, but the farther away they are, the faster they are flying away from us. In fact, Hubble found that for each additional megapark of distance, galaxies receded 500 kilometers per second faster. This became known as the Hubble constant, and the area of our observable universe is called the Hubble volume. One thing we need to understand is that the word observable in this sense doesn't refer to the capability of our current modern technology to detect light or other information from an object, or even if there's anything to be detected. Observable here in this case refers to the physical limit of the speed of light itself, which is its maximum speed. When talking about the distance of anything in space, we're also talking about time. Looking up into the night sky is a little bit like time traveling. All those glittering stars in the night are only snapshots of what those stars look like in the past. Just think about it. Some stars and other objects in the cosmos are so far away that their light can take thousands to millions of years to reach planet Earth. And if there is something beyond the edge of the observable universe that we can't currently see, it means that these objects are so far away from us that their light still hasn't reached us. The cosmic horizon is a measure of the distance from which we can retrieve information. But is there something out there past what we can see? It's really tough to answer this. However, to get some idea if there is something out there, we need to take into consideration the curvature of the observable universe. The thing is that astronomers aren't really sure if the universe is infinitely big or just vastly huge. In order to measure the universe, astronomers look at its geometric curve on large scales, which tells us about its overall shape. If the universe is perfectly geometrically flat, then it can be infinite. But if it's curved like Earth's surface or is like a bubble, then it is finite volume. Current observations and measurements of the curvature of the universe show that it's almost perfectly flat like a sheet of paper. That would indicate that it must go on forever. We know with some certainty that there is more universe out there beyond the boundary that we can see. Astronomers believe that space could be infinite with more of what we already see, and it's probably distributed the same way as it is here in the observable part. Now, here is one of the mind-blowing things to think about if the universe is infinite. If this were to be true, then you wouldn't just find stars, different planets, and galaxies. You would eventually find every possible thing. Think about that for just a moment. You would find everything. If you went far enough, you would find a solar system identical to ours in every way. including a planet Earth and your twin. Except that a copy of you might have eaten cereal this morning instead of a version of you that skipped breakfast altogether. It's a fact that some cosmologists think if you go far enough, you would eventually find another Hubble volume that is identical to ours with a version of yourself mirroring your every action. Now, while that might sound impossible to what our minds can grasp and understand, there is something else very strange and unexpected that was discovered by astronomers in 2008. They found that galactic clusters were all streaming in the same direction at over 3,218,688 kmh. It's a phenomenon called dark flow. This movement of galaxies defies all predictions about the distribution of mass throughout the universe after the Big Bang. So what is a mysterious gravitational pull on all these galaxies? One possible cause could be massive structures that are outside of the Hubble volume that are exerting a massive gravitational influence. In simpler terms, massive objects with a huge gravitational force pulling everything towards them. If true, this would mean that the structure of the infinite universe beyond our view is not uniform. No one knows what these structures could be. It's possible they're aggregations of matter and energy on scales we can barely fathom. Or they could be gravitational forces of other universes. Speaking of massive structures, there's one in our universe that's so big that it shouldn't even exist. In fact, it's the biggest structure in the observable universe. It's called the Hercules Corona Borealis Great Wall, and it measures 10 billion light-years across. It's so big that it makes up 11% of the observable universe. To put this further into perspective, if you were traveling at the speed of light, it would take you 10 billion years to get from one end to the other. So why shouldn't it exist? The problem is that astronomers have no idea how this great wall formed only a few billion years after the Big Bang and could have grown so big in such a short time. This means there could be giant structures like these out there pulling on everything, including space. One day, it could very well rip apart the fabric of space-time itself. And speaking of gravitational forces from other universes, some astronomers believe that the post-Big Bang expansion of the universe created bubbles that formed in the structure of space. And each of these bubbles is an area that stopped stretching along with the rest of space and formed its own universe with its own physical laws. In this scenario, not only is space infinite, but each bubble is also infinite because it can store an infinite number of infinities inside a single infinity. To make that seem a little more clear, even if you could breach the boundary of our bubble, the space in between bubbles is still expanding. So, in the reality of space-time, you could never get to the next bubble, no matter how fast you traveled. But will we one day have the technology to see what is beyond the edge of the universe we can now see? The sad reality is that light from any object outside the Hubble volume will never reach us because the space between us and it expanding too quickly. For example, we may never see what a galaxy looked like 10 billion years after the Big Bang. This doesn't have anything to do with our limited technology, but instead the physical limits of the speed of light itself. This means that any light emitted by objects at a distance of 19 billion parasecs will never reach the Earth. As time goes on, more and more points in space will have time for their light to reach us, which means that the observable universe is still increasing in size. And that also means that the age of the universe will increase. That said, you might think that one day, if humanity is around long enough, the entire universe will become observable to us. But since space in the universe is continually expanding, the distance between us and everything else becomes farther and farther each second. However, the James Webb Space Telescope will be able to look farther into space, will look backward in time, and just may give us more answers to what else exists out there. In a sense, it's a time machine, and we'll be able to see further into the past. With that said, we want to know what you think is out there. And do you believe that the universe is infinite and there's someone just like you somewhere billions and billions of light years away? Let us know what you think. And if you have any ideas on what you'd like to see next, then let us know. Thanks for watching Dark Core.